Okay, let's summarize the characteristics of the logarithmic function. So we've got, the definition of a logarithmic function is f of x equals log of x base b, where b is greater than 0 and not equal to 1. And so first we note that the domain when the function is in this form is 0 to infinity, and the range is all real numbers. We have three special points. And those special points are 1 over b negative 1, 1, 0, and b 1. We now have a vertical asymptote of x equals 0. And before I move on to the next couple of characteristics, note that in each of these three categories here, it's really just, we've just inverted the x's and the y's. So the domain of an exponential function is really equal to the range of the logarithmic. The three special points, if you know the three from the exponential function, then all you need to do is swap them to get your logarithmic. And the horizontal, you have a horizontal asymptote for an exponential function of y equals 0, and it's x equals 0 for a log function. What we also know is that, and this is true of both, that when b is greater than 1, the function is increasing, and this is true for both exponential and logs. And when b is between 0 and 1, in other words a proper fraction, both logarithmic and exponential functions are decreasing. And then the last thing is true of both, that it is a one-to-one function, and therefore it has an inverse. So let's quickly kind of just recap the graphs. So when b is greater than 1, you have an exponential function is increasing, so is the logarithmic function. And you can see that when they are graphed together, you get that nice symmetry over the line y equals x. Okay. If we then come down and look at the scenario where b is a proper fraction, so a value between 0 and 1, that both the exponential function and the logarithmic function are decreasing. And again, we can see that symmetry over the line y equals x when you graph both of them on the same coordinate axes. Okay, so now that we've got the basic idea of how to graph a log function, let's graph a transformation of a log function. And basically, once you understand transformations of any function, as long as you know how to graph the basic graph, then you use those same concepts to graph any transformations. So to graph the log base 4 of x minus 2, I would first graph my basic function of log of x base 4, get the three special points. Again, if you want to revert all the way back to an exponential function, you can do that, or we can just focus on those three special points of a log function, which are 1 over b, so 1/4, 1, 1, 0, and b, or 4, 1. That should be a negative 1, sorry about that. 1/4, negative 1, 1, 0, and 4, 1. And we have a vertical asymptote of x equals 0. Now to graph y equals the log base 4 of x minus 2. Think about what type of transformation that is. Subtracting 2 from inside is going to be a horizontal shift to the right. We're going to add 2 to each x value. So the y values are going to stay the same. I'm going to add 2 to each x, so 1/4 plus 2 is 2 1/4, 1 plus 2 is 3, and 4 plus 2 is 6. And also, since I'm adding 2 to every x, I also have to add 2 to my asymptote value, so it's going to be x equals 2, shifting everything over. So 2 1/4 down 1, 3, 0, and 6 up 1. I have a vertical asymptote that has been shifted over 2 units. I'm going to draw that in. and then I'll try to connect these with as smooth a curve as I can, approaching that vertical asymptote but not hitting it. Before I graph the next one, let's state the domain of this function. So, in the range. So the domain, since if it's shifted over 2, it's going to go from 2 to infinity, the asymptote being the smallest value that, well, it actually approaches it but doesn't hit it. And the range is all real numbers. Right, now let's move on to graphing the natural log of negative x. So let's first graph, or at least get the ordered pairs for, the natural log of x. So we would want, remember the base is e, it's implied, so I'd want 1 over e negative 1, 1, 0, and e1. And remember, 1 over e we said was around a third, or pretty close to 0.3. E is actually equal to 2.7, approximately. And so if I want to graph f of x equals the natural log of negative x, I'm replacing x with negative x, so I'm changing the sign of all of the x values. And so this is also going to should give me a reflection over the y-axis. So I'll state my 3 new order pairs. So I'm going to change the sign of all the x's. So I'd have negative 1 over e, negative 1, and negative e, negative 1, 0, 1 for my y's. And remember, this is around a third, so it would be negative a third, and this is around 2.7, so it would be negative 2.7. My asymptote for the original is x equals 0, and reflecting over the y-axis does not change your asymptote. So around negative a third, down 1, negative 1, 0, and then negative 2.7, up 1. My vertical asymptote is the y-axis still. I come through these points gradually and try to approach that axis without hitting it. Okay. The domain, in this case, since we've reflected it over the y-axis, it's negative infinity up to but not including 0. And the range would be all real numbers. So the range for all logarithmic functions is all real numbers.